yourself, it is full of analog systems only. Naturally, what you find the signals and the most common things what you have around you, those are all mostly analog. Now, if we have moved to digital, there must be some problems associated with the analog, right? Why we are going to digital if the world is full of analog signals? Why we need to have digital? What is the purpose of having digital? Or what advantages does it give over analog? So we need to go for digital kind of system and digital signals and all these things. And before that, we will try to understand what is meaning of digital. So let's first understand the disadvantages of analog system. Now, what could be a typical disadvantage of analog system? Any of you?
Sir, was it the cost of running at the time?
Yes. Cost of running. But if you be more precise, then you can come to the exact answer. This is very, very close to the exact answer.
Sir, heating conditions.
Yes, that is leaking condition is one thing. What else?
So noise, we cannot we cannot correct errors in analog. It's very difficult. Whereas
less efficiency.
Less efficiency, another very, very close term. And then accuracy is poor. This is another very, very close thing. But why all these things are coming?
It doesn't have properly defined on and off system.
It is?
It doesn't have any properly defined on and off system.
Yes, that is why it is analog. It's not having the defined states. It can vary anywhere between the given range. That's why we are calling it analog. But why all these things are getting associated with analog? What's so special?
Sensitive to the environment.
Hmm?
So it is highly sensitive to the environment.
Yes, but why?
Sir, it is very random.
No, that's not the answer. Why do you say it is random?
Because semiconductors are used, I guess.
So all the variables are dependent
on what?
On one basic condition which can be considered either voltage or.
Yes. This is another close thing. So, for example, if I talk about, let us say, electronic devices, because of course we have resistor, capacitor, inductor, and all these things, but this is not all for the analog circuit. We have electronic devices such as BJT or sometimes the FETs. All these things are there which are part of the analog circuit. Most importantly, the BJT. Now, when BJT is operating for any analog circuit, it typically operates in the linear zone of operation here. Depending on the IV, different values it can have. Now, what is the problem when it is operating there? What's the problem when it operates over there? This VC voltage or this current, which are basically dictated by IB and the external circuits. So these are something like moderate and significant values. Let us say if you talk about the current, depending on what kind of application you are having, this could be like few amps if you are having bigger system. And VC, depending on, let's say how big your system is, it could be 5 volt or something like 10 volt. That also it could be. Now you imagine about the power loss happening in this device. What is the power loss now? Let's say you consider 10 volts and 2 ampere, 20 watt power loss is happening in just one device. It may look like a small power loss to you because practically, no, when you don't see it, you don't realize how big this power loss is for such a small device. Okay, continuously, if we are having this kind of power loss, the temperatures may go very high and it may eventually damage. So what people would do if let us say they cannot avoid this, so this is typical example of audio amplifier, where you have the BJT, you are giving the control signal here and you are getting the output over here. So when people cannot avoid this power loss, what they will do? They will have to go for bigger devices, bigger size, so that the power loss can be managed. They are managing only bigger surface area, bigger area which is exposed to environment, so it can manage the heat whatever is dissipated in the device. Understanding my point? And then
Yes.
all the associated things, the efficiency, cost, and no, it is prone to noise and disturbance and all that, everything comes in this. Efficiency is low, of course. Then cost is high because we are having more size unnecessarily just to manage heat. It can manage the same voltage, same current with much smaller size, but it can't manage the power loss. So that's why we need to go for bigger devices. So typical old systems, if you see, whether the audio amplifier or all these things, you will see very big size. So that big size reflects something that, and it will get heated up very heavily. If you touch it, it will be very hot. So these are the reasons. And then imagine if there are 10 such devices operating in parallel, 200 watt of power loss you are having in just one system. So the scalability is also questionable. If you have 10 devices, you cannot make it simply 20. The power loss will double, or maybe it may go more. With temperature, the properties may change and it may start having more losses. So scalability is another question. Then accuracy. When you talk about these devices having so much power loss and all, of course, there could be some noise sitting on IB and then that will be reflected on VC. So everything is amplified. What input you are giving is amplified. So the noise which is going, that will also be amplified. So you need to have very accurate control system, some feedback control or something to manage these things, to cancel out the noises. So it's huge challenge and it is varying. There is no defined state. So it's going continuously in this manner. Now any noise sitting in on this may distort it like this.
Yes.
Understanding my point? So these are the drawbacks. So scalability, cost, efficiency, noise, accuracy, all these things are associated with the analog systems or analog processors or computers or anything you want to name it. So that is why with time we realized that no, we should have some other mode of processing these signals and computing our signals and then doing the control. But the final output, because we live in this world where things are analog, so we will have analog input at the very initial stage and we will have analog output at the very final stage. But in between, all the losses and everything we can take out by converting everything to digital. Am I clear?
Yes, yes.
Any questions up to this? Any questions?
Can you take some examples, sir, of this?
Of what?
Analog to digital and last final.
Yes,
result.
yes, we will come to that. Before this, now we are going to start something else. So I want up to this if you have any doubts. This whole course we are going to do this thing only. So don't worry, plenty of examples we will have. Okay, now first we need to understand what is the meaning of digital. Okay, before that, just let me check if I'm missing something. Okay, maybe one more thing we can add is that when we talk about the signal, there is no restriction on how fast the signal may change. So xt, when you say, it could be sine 100 pi t. So this is a 50 hertz signal, and you may have some sine, let's say 10,000 pi t. These both are like your analog signals. Understanding my point? Whether it is 50 hertz signal or 5,000 hertz signal, it's analog still. So how fast it is changing, that does not make it analog or digital. It's only the continuity. Clear? Clear? Yes or no?
Yes, sir.
Yes, sir.
Now let us come to what do we mean by digital. So any answers?
Any two states,
Hmm.
any two specific states of
What is so special about two?
digit.
What is
So
why
something that can give
states?
us accurate value.
No, that is true. We can have three also, no? Three states giving the accurate value. What is so special about two?
So because we can just consider it as yes or no,
Yes,
highly
this is one
specific.
good answer. But what else? This is something more physical than philosophical. That
On and
answer
off.
So we can have an on and off state.
very good. Very, very close to this. But on and off of what?
On and off of a device.
Say again, Krishnabhushan.
On and off of device.
Okay, which device?
Sir, working of the system, whether it is on, whether it is in the on state or
When
off
you
state.
say system, what do you mean by system? Fan is also a system. But yeah,
So whether a system is present or not.
that is true. But what can you tell more specifically? What do you mean by device or system or something? What is getting on and off?
The input and output signals.
Input and output signals. Okay. Something else I want actually.
High voltage and low voltage.
Check current. Flow of current.
High and
No,
low.
no. See, you are deviating. You were very close. When you say device, you should have said
transistor.
yes. For example, BJT. So why we have two states only? Why not 3 or 4 or 5? When we have 3, 4, 5, we can be more accurate, no? Instead of 2, either you have 0 volt or you have 5 volt. Where is the accuracy? Accuracy is lost actually. Then analog was better. No, it was giving you everything between 0 and 5. So in fact, we are going in other direction. We are going inaccurate. Then how come digital is superior?
So accuracy is lost, but the signal which we want, we are receiving it easily.
How? Let us say I have a sinusoidal signal varying between 0 and 5. What will you get if you have only 0 and 5 states? Either you will have 0 or you will have 5. How come this is close to sinusoidal? Is this close to sinusoidal? It's very far.
So, but in some cases, we do not need to know the range of values. We just need to know if the device is on or off.
Yes. But what is that condition? When is it okay to just know the state, irrespective of the value? When is it all right to do?
When there is a specific threshold that after this threshold the device will work or not.
Correct. For example, if let us say, simple example, if any overhead tank is there, water tank, and you want it to be full whenever it is below some threshold value. So this can be done with some on-off switch. Whenever the water goes below this level, you turn on, and whenever it touches the top level, you turn off. This could be two state only. Either the motor is running or it is not running. The pump is running or it is not running. Isn't it? But this is something very crude. How about the computations? How about having more accuracy? All these things. So before that, let us first understand what is so special about these two states. Why not 3, 4, 5 or something else? So let us see the nature of BJT. What we have seen is only one part of BJT characteristic. Now, our device has actually 3 states in which it operates, no? So I am intentionally making this little bit bigger because this has some value. So anyway, you can have more steeper and more accurate waveform, but that doesn't matter. So 3 state when we talk about, no, one is linear, in which our analog devices or analog systems are operating. The other 2 states which are useless for an analog system are like saturation mode. And the third is cutoff mode. So saturation mode, when we say the device voltage has saturated, correct? It is like the base current is too high. And cutoff mode, when base current is not sufficient to cross that threshold. So what is the speciality about these 2 states? Of course, it is useless for the analog system. But what advantage it gives? The VCE voltage, the drop across the device during the saturation mode is very, very small. Let us say 0.2 volt or 0.3 volt or something like that, irrespective of the size of the BJT. It could be even smaller for some special designs or lower size of the BJT. But even for very big BJTs, power BJTs, the number doesn't increase so much. And in the cutoff mode, this IC is 0, very, very small, maybe some microampere, some leakage current is there. Now the beauty of these 2 states is that power loss is how much? Very, very close to 0. Or at least to say, compared to the analog or linear mode, it's very, very small. Where we had some 20 watt, here it could be maybe 2 watt or 1 watt or even lesser than that for better design. So eventually we move to FETs where we have even better. So this is typical MOSFET. So here we have even better results for that. So this is one greatest advantage what we get when we operate our devices in these 2 states only. So the first one we call is on state. What is meaning of on state? On state means the device is allowed all the current to flow through this. It is not putting any resistance or any kind of hindrance to that. So it is like a switch which is now connected, which is closed. And when we say cut off, the switch is now in open state. So it's not allowing any current to flow through this. Now when we have these 2 things, we can call this as on off or yes no or 1 0 or anything. But again the question comes, how are we anyway improving on all those disadvantages which were associated with the analog systems? So let me go back and see what were the disadvantages, or can you name it quickly? What was the first disadvantages? What was the first disadvantage? Efficiency.
Yes.
Then next one.
Cost.
Leaking.
Cost. Then.
Cost of running.
Then.
Scalability.
Scalability. Next.
Accuracy. Yes, presence of noises.
Then.
Leakage.
Noise immunity, we can say. Fine. Anything else we are missing out? Fine.
Yes.
This is very, very straightforward visible that yes, now we have much better efficiency compared to the analog systems because our power loss is significantly reduced. Isn't it? Yes or no?
Yes, sir.
You have to respond.
Yes, sir.
Please remember. Then the next is cost. I told you that the device size even very small device size is sufficient to manage that voltage and current whatever we want. But it is the power which actually forces the manufacturers or the designers to have bigger size, bigger surface area and all that. Now once the power loss is lesser, we can have smaller size. So that's why you will see that nowadays the chip size is reducing every day. It is like significantly shrinking. Whatever we used to have, no, this 5 MB storage some years or decades back, that used to be of this room size. But nowadays you will find 5 MB is what? You can have 5 terabyte and all within just a small, no, this pen drive or something, or a small disk, hard disk. So it is all happening because the cost has reduced, and so we can shrink the size. Power loss has reduced, so we can shrink the size. Again, scalability is very much related to, if let us say the same chip, we are able to reduce the size and the power loss is also not significant. Of course, we can increase the number of chips what we can accommodate in the same area without having any significant problem with the performance or anything else. Now this part, accuracy, we will come last. Next is noise. Now when we talk about analog signal, typical, let's say this is the analog signal, and any noise sitting on this may look like, correct? Whereas digital signal, when we say yes or no, that's what we have seen, or 1 or 0. This is the two possibilities we are finding. Let's say this is one typical digital signal. It's having either 1 or 0. Now, irrespective of what noise is sitting on this here or here, the value here is 1. The value here is 0. Whereas here the value which was, let's say 3.5 volts, now it may be 3.7 volts or sometimes 3.3 volts. So the inaccuracy of 0.2 volts we are having just because of noise. And here it is not getting disturbed. Of course, we have a band over which we say that this whole range is called as 1. This whole range is called as 0. Because we have only two possibilities. Understanding my point?
Yes.
So this has a very great noise immunity. Now, what about the accuracy part?
Sir,
Yes. Yeah.
the noise will not disturb the state 1 for the device. That's why the noise effect is eliminated.
Yes.
Okay, sir.
I'm not saying it will not affect. If let us say some noise, if you can imagine is something of this order, it will disturb everything. So it's only relative to your signal. What is the value of noise? So
Error is small.
10% of noise will not affect. But if it is varying, comparable to 50% of the signal, this thing values, then of course it will affect. Clear? Now, when we talk about accuracy, what is the meaning of that? So here, one thing we have to understand that when we are having all analog signals, let us say something like this, and we want to process this signal in the digital domain with the digital processors, digital computers, how do we do? What is the mode of processing this kind of signal with an digital computer?
Cutting in very small parts.
Yes, that is to say in a crude manner, but a more technical term is sampling. Sampling means that we are perceiving this data only at regular intervals. Or another word to say is that we are discretizing the signal. So now this analog may look like something like this. And it depends on how fast you are sampling. There are certain rules associated with the sampling. You cannot just sample at one end over here and one end over here. No, you will lose significant amount of data. So when we are sampling it like this, what we are doing basically, we are having some values of this signal for the certain durations. Now, when I say accuracy, what I mean by is that we are representing this data, whatever we have perceived, that data we are representing accurately in the digital domain. So let's say you want to represent 3 volts. So that is the value, let us say over here, the value is 3 volts. So 3 volts, how can you represent? You have only 1 or 0. Now let us say, little bit I will go ahead in the syllabus. Let's say you take 4 devices which can have either 1 or 0. And you somehow code that, okay, if all devices are having 0000 value, which means it is 0 volts. If the devices are having 0001, that means it is 1 volt. If the devices are having 0010, that means it is 2 volts. So now we are having accuracy for every 1 volt. Getting my point?
Yes.
Now, if you scale it, let us say instead of only 4 devices, you make 16 devices. So you can go for even much more better accuracy for a range of 0 to 5 volts. So you will have 2 raised to the power 15 divisions or 16 divisions for this 0 to 5 volt range. And every bit or every number what I say over here is having the same immunity towards any small noise coming on the system. Understanding my point?
Yes.
So this is the way we are making our system accurate. We can scale. So one option is have only one device. Either it can have 0 or it can have 1. So which means 0 volt or 5 volt. Or you can have 2. So 0 0 or 0 1 or next state could be 1 0. These are the possible combinations. We will discuss about these more, but these are the possible combinations. So 5, no, you can do something like, 0 into 5 by 4, 1 into 5 by 4, something like that we can do. So ultimately it will have 5 volt and in between some values. So a little more accuracy, then 4 will give some more, 16 will give some more, like that you can have. So this is what I mean by when we say the accuracy. Am I clear?
Yes.
Yes, sir.
Yes, sir.
Or it's going above your head little bit now?
Sir, I have a doubt. Sir, like in this manner, we can make our signals more accurate. But
Yes.
if we are making the signals more accurate, aren't we making it more vulnerable to noises?
Say again.
Are not we making it more vulnerable to voices in this way?
How?
Now the sensitivity is more, like sensitivity is very much increased. Now at only 0.25 volt, the signal is varying, digital signal is varying.
Correct,
So the
correct.
noises are now even short na signals.
Correct. So let's say you have now the capability to have accuracy of 3.0000001. This level of accuracy you have achieved with, let's say, some 16 devices in the system. So does it matter if this digit changes?
No, sir.
If you have only this much accuracy, if this changes, will it be significant? Yes or no? Which is more significant? Which change is more significant?
The later one.
Correct. So by increasing the accuracy, you are actually, because every set or every device or every number is something like this 0 or 1, right? So each one is having the same immunity, and in fact any disturbance coming on the lowest or the first, the rightmost side bit, will not affect immediately this bit. Only when all these things change, then only the next one is going to change. Isn't it? Let's say everyone is erroneous, everything is wrong, then only this may change its value. And immunity towards the noise for each and every bit is almost same. So it's actually better. We are going for more noise immunity. Am I clear or not?
Yes, sir.
Clear? Any questions, anybody?
Sir, by making more bits for discretization, we are not making the signal same the analog as before.
Yes, clear. That is what we want. Because nature is having analog signals. We want to perceive that as digital. So we have to keep it very, very close to what is available. And when we are giving output, then also we have to be very, very close to what the word knows. If you are speaking in some digital audio amplifier, what it is giving as output should be close to your voice. It cannot be computerized so much. Getting my point?
No, sir.
Why? What's the doubt in this? What's the doubt, Rajendra?
We are perceiving analog signal, and with the help of this digitalization, we are making the same analog final.
Yeah.
Then what is the what difference we make by using this?
Okay. Anybody? What difference are we making? Anyone?
We are reducing the disadvantages we faced in the analog signal.
Exactly. Why we are doing digital and all this? Because we want our processors, we want our systems. So basically, we are not making our fan digital or something. It's only, let's say, the controller or how it is taking our input. That processing thing we are doing in a digital manner. And that is where we need to interface. We need to interface our analog signal with the digital system. And this is where we need this kind of transformation or conversion. And again, when it is giving output, a one more level of conversion we would need. But these are all necessary to reduce the burden and size and cost and improve the efficiency and accuracy and improve the noise immunity. All these things are necessary. So we are making our computations more and more accurate. That is the whole idea. Clear?
Yes, sir. Yes, sir.
Okay.
Excuse me, sir.
Yes.
Sir, digital is less accurate than analog now because we are trying to approximate it. So we are trading accuracy for power loss like that.
Good question. Okay. Now x equal to sine omega t is, let us say, a sine wave. Right? Correct? Yes or no?
Yes, sir.
Now tell me how accurately you can represent the values on this sine wave. How many data points you can write for this?
Infinite.
Can you write? There could be infinite mathematically, but can you write? Can you write?
No, sir.
So analog is something, what I say, analog or a continuous system or perfectly varying system, I say, is more theoretical. In a real world scenario also, we cannot perceive these kind of very, very continuous signals. Of course, we will be giving some accuracy. Let's say accuracy only up to 5 digits. No, even if I ask you what is value of pi, I don't know up to what number you would say, but still that would not be exactly accurate as pi. Isn't it?
Yes, sir.
So what our attempt is, we want to keep our this digital system as close as possible to our analog input and whatever we are processing, as much as possible. Now that accuracy again depends on what you are doing. If let us say in a calculator you are doing 2 plus 2, the accuracy doesn't matter. You cannot say 4.000000 and so on. You cannot say that. It's 4. But yes, if you are doing some heavy computation and you are simulating the track of any satellite or something, or you are simulating some other this missile or something, how it will trace its path and all. So even a small error at the 10th digit or something may change everything. Or if you are predicting the weather or something, even when a small tiny bit of change at the 10th or 20th bit may change everything. So accuracy matters where it is needed. So based on what we are dealing with, we have to go that much accurate. We are happy with saying pi equal to 3.14, but any mathematician will only shout at us saying that what is this? At least you can say 22/7, but that is also very, very inaccurate. Understanding my point?
Yes, sir.
So that is how, yes, we are making inaccurate. Now, any real world signal also, when we say it is continuous, it is analog and all that, is it really analog? It is really varying continuously?
It should, right?
It should, but is it? Go in the details. Your temperature is changing, but is it changing every order of 10 raised to power minus 12 degrees centigrade or 10 raised to power minus 15 degrees centigrade? Is it taking each and every value really? Or your speed is increasing at every, let us say, 10 raised to power minus 20 kmph? Is it increasing
Sir,
like that?
theoretically it should, but we don't care that much.
But it cannot. So that is why I say we are having a mix of these things even in the real world. Of course, this discretization or this sampling is very, very small, very, very minute. What you are seeing, let us say, that is also frame by frame you are perceiving. It's not the continuous film you are taking. It's only the frame by frame processing you are doing. But the time duration is so small that we don't see it like a picture. We see it like a video. Understanding my point?
Yes.
Yes, sir.
So, word itself, and the best example, how can you forget? Light. So when we talk about the quantum particles, light, electron and all that, what do we say? They all have dual nature. They are waves sometimes, which means continuous. They are particles sometimes, which means discrete. Isn't it?
Yes.
So it is our perception. Anything what we are doing is our perception, our computational efficiency and our computational ease, what we can do with easiness. Oh, that information if you are storing, and if you have that old audio tapes or video tapes, I don't know if some of you have seen or not. So maybe before, when you must be very young or before your birth, those days, they used to have big tapes. Nowadays, everything is available in just a small disk, or even that also you don't need. Everything is available digitally. So that is how world is changing. That is our perception. The information is same. But how we are storing it, how we are processing it, how we are perceiving it, that is changing everything. Now, because we have said that, okay, when we are going to digital domain, we have on and off, or 1 or 0, or yes or no. Isn't it?
Yes.
These kind of things we have in our digital domain. So obviously, if we have a number system of what we use in our day-to-day life, say the base of 10, So we cannot represent these things very well with this number system. So anything we are sampling or we are processing or we are doing, we must have a way to represent it. And that representation is basically why we go for the base value 2, because there are actually 2 states. And then all other multiples of 2 because we want to have more accuracy and all these things. So this is where the special number system starts, which we will be seeing in the next class. Fine?
Yes, sir.
Any questions, any doubts up to this point?
No, sir.
So I hope you are getting the idea why we are doing this course.
Yes, sir.
Good. Okay, then we can stop over here. There are no more questions.
Sir, excuse me, sir.